The fuselage is the central section that holds all of the pieces of the airplane together, as well as being where the passengers, cargo, and some of the fuel is located. The jet engines are the machines that generate thrust for the plane, located either under the wings or near the tail section, that power the aircraft to a speed at least sufficient to gain altitude. The wings generate most of the plane's lift, contain fuel in many cases, and house both the engines and several aerodynamic components, which increase performance and efficiency. Some of these systems include slats, which increase lift for landing and takeoff, spoilers, which increase lift and drag for landing, and flaps, which increase lift drastically at the cost of drag. To control the airplane's motion, various devices can be used for differing purposes and functions, including the ailerons, which change the roll of the aircraft, the vertical stabilizer, which controls the yaw of the aircraft, the rudder, that changes the yaw of the aircraft, the horizontal stabilizers, which control the pitch of the aircraft, and the elevators, which change the pitch of the aircraft and produce lift, usually negative, in order to counteract the massive positive lift produced by the wings. The rudder is an example of an aerodynamic device which from a fluid dynamic standpoint works differently than one would expect. The side-to-side movement of this surface changes the distribution of pressure on it, with a modification to the right producing a high pressure on the same side, thus pushing the tail to the left. We can now look at two main aircraft components in a little more detail, being the engines and the wings. Beginning with the former, the main kind of propulsion used nowadays in commercial aircraft are gas turbine engines. This is due to their ability to have a combination of high power, reliability, and fuel efficiency, meaning that they are the best solution for many manufacturers when designing their planes around them. From a physics standpoint, these engines work by using Newton's third law of motion, that states that for every action there is an equal and opposite reaction. In fact, air enters the engine and is accelerated by various systems and reactions. Gas then exits the engine at a very fast velocity, producing thrust and movement in the opposite direction. The amount of thrust generated depends mainly on the rate of mass flowing through the engine, and the final exit speed of the gas, with more opposite force equaling more propulsion. Most of the jet exhaust mass comes from the atmosphere, including substances such as carbon dioxide, water vapor, nitrogen, and oxygen, as well as other byproducts from the reaction processes, such as nitrogen oxides, soot, and carbon monoxide, all toxic and harmful. As for airplane wings, we can look at their structure and the names of the main points of interest. The forwardmost point is called the leading edge, while the aftmost point is the trailing edge. The imaginary line connecting these 2 points is called the chord line, with the angle of attack being the difference in inclination between the wing's chord and the oncoming flow. Camber is the curvature of the airfoil, which varies from aircraft to aircraft depending on their characteristics and aerodynamic requirements. It is used to increase lift and at the same time reduce the stall speed of the airframe. A wing with zero camber is symmetrical and has a horizontal chord line. The aspect ratio of the wings is the relationship between their length and width, with higher aspect ratios usually meaning a better efficiency in creating lift. The wing area is the total surface area of the wings, with a greater value also signifying a greater ability in creating lift. Slats and flaps work by increasing wing area and angle of attack, in turn increasing the airfoil's lift. The equation for lift contains the variable CL, or the coefficient of lift, which is used by engineers to convey the relationship between all of the factors affecting this upwards force, except for the wing area, which has its own variable A in the expression. After looking into the main parts of an aircraft and how they function, we can look into the 4 aerodynamic forces which act on these vehicles. The first and most obvious one is weight, which acts perpendicular to the plane and is directed towards the center of the Earth. The total weight depends on factors such as payload, fuel on board, and the weight of the airplane, while empty and unfueled. The weight is distributed throughout the airplane but acts as a force through the center of gravity, which is the average location of the weight along the aircraft surface. In flight, weight and its distribution are in constant change due to factors such as fuel burn, causing the airplane to have a shifting center of gravity. This variation affects performance, with all the aerodynamic components, including airfoils, being modified to maintain balance. As we know, lift is the vertical force that is created by airfoils, and is in fact the opposite force of weight. Lift is always perpendicular to the flight's direction, with this force depending greatly on factors such as the weight, speed, and size of the aircraft. Similarly to weight, this force acts for an average point known as the center of pressure, with its location changing constantly along with the center of gravity. The distribution of lift along the aircraft is altered by the airfoils and aerodynamic surfaces in order to maintain level flight. Drag is the resistance the airplane encounters when penetrating the air, and acts as a force along the direction of the fluid's motion, but opposed to the course of the aircraft. Factors affecting drag include the viscosity, or stickiness, of the gas molecules in the air, as well as the overall shape and speed of the aircraft. There are 3 main kinds of drag, being parasitic drag, induced drag, and wave drag. Parasitic drag is composed of other aspects of air resistance, namely, form drag, caused by the shape of the aircraft, skin friction drag, caused by the smoothness and texture of the aircraft surfaces, and interference drag, caused by the meeting point of surfaces with differing characteristics, for example the wing and fuselage. Induced drag is caused by the production of lift, while wave drag is instead related to the formation of shock waves near the aircraft's surface, but only in transonic and supersonic flight. As with lift, drag acts for the airplane's center of pressure. Thrust is the opposite force of drag and is created by the propulsion system of an aircraft to overcome air resistance. In commercial planes, the jet exhaust is normally directed in a direction opposite to the aircraft's motion, providing power in the required direction and thus counteracting drag. Additionally, many airframes have the option to invert the direction of this force, creating reverse thrust and thus assisting in the stopping performance of the plane while landing. Factors affecting thrust include the type of engine, the number of engines, and the thrust setting. The purpose of thrust is to get the wings to a speed sufficient to overcome weight through the creation of lift, although thrust does not directly influence climb performance. Due to lift and drag both being aerodynamic forces, engineers use the lift-to-drag ratio to measure aerodynamic efficiency. An aircraft with a high ratio produces a great amount of lift or a low amount of drag, while the opposite can be observed in a plane with a low ratio. A high-lift plane can carry larger payloads, counteracting weight, while a low-drag one can operate with less thrust. In airliners, less drag means less thrust needed, which in turn signifies less fuel needed and a consequent longer range. The thrust-to-weight ratio is instead used as a measure of the propulsion system efficiency of an aircraft, and is directly proportional to the acceleration of the plane. A high ratio means high acceleration, high excess thrust, and a high rate of climb, with values above 1 and very low drag, meaning that the plane is able to take off vertically. The aircraft's thrust-to-weight ratio is more important than the engine's, due to the former measure giving a better picture of the airframe's actual performance. The thrust-to-weight ratio is given at sea level, due to increases in altitude negatively impacting engine performance.